KK-equivalence.
Thanks for inviting me to this online conference. And I have added 2 additions to my title. I didn't want to make it too long, but of course, classifying C-star algebras, just C-star algebras isn't so interesting. You know how to do it. So the interesting things come in if you add extra structure to them, like for instance, a group action, or maybe some specific ideal structure. And then there is a suitable equivariant KK theory, and you want to classify them up to equivariant KK equivalence. Why is it so important to aim for equivariant KK equivalence? Well, if you impose some analytical extra assumptions, then from there you can actually go much further. So there are some deep analysis results which say, under some extra assumptions, KKG equivalence implies more. Something like, let's say, an equivariant Morita equivalence. So you can get some stronger result if you look at the unit element, then you might even get isomorphism. But let's not worry about this. So for me, KKG equivalence just means what it says. I don't look at the unit element, and then, well, clearly you can't distinguish, let's say, between the complex numbers and the matrix algebra over it. So you can at best get equivariant Morita equivalence out. For instance, this is what happens if you look at the classical result of Kirchberg-Phillips, purely infinite separable simple nuclear C-star algebras. But there is also a version of that result if you fix the ideal structure. So the C-star algebraic way to do this would be so I'm taking 2 C-star algebras that have the same primitive ideal space. So this is a topological space with a suitable topology. This is equivalent to having isomorphic lattices of ideals, closed ideals, that is. So these are isomorphic as lattices. And then any equivalence between them in KK, well, I should have written just X here. So what's this? This doesn't work on this screen. So if they are equivalent in this KK theory, and I should add some more adjectives here, purely strongly to infinite, and there's nuclear separable is also required. So then a deep result of Kirchberg says that you can actually get something close to an isomorphism, a Morita equivalence, if you know that they are equivalent in the suitable version of KK theory that takes into account the ideal structure. This is like an equivariant KK theory where you restrict to some kind of KK cycles that are compatible with the ideal structure in a certain sense. You might wonder, what does strongly purely infinite mean? And well, maybe a good definition would be just O infinity absorbing, meaning that if you tensor with O infinity, then they are the same. And if you add stable, so which means compact as absorbing, then you also get isomorphic in the end, because Morita equivalence in this class of algebras is the same as stable isomorphism after tensoring with the compact operators. And so if you're already stable, then this is just isomorphism. Okay, so if you want to use this result, you need to be able to decide whether two C-star algebras with given primitive ideal spaces are KK equivalent, if you know that you can produce an isomorphism between them, or at least a Morita equivalence. I got into these questions shortly after working with Richard on the Baum-Conn conjecture. Of course, I noticed that there is some similarity with the usual UCT. So some of the methods I developed could also be used to understand the universal coefficient theorem, which is just for KK theory. And when I was visiting Richard in Copenhagen to, well, talk about these things, I also chatted with Michael Rördam, who was interested at the time in the classification of graph C-star algebras. So these are more general, non-simple C-star algebras. So, and the question was whether you can prove some results using my method. And at first I thought, yes, of course, we can do it. And then later I found it wasn't so simple. And so a number of papers later, we have a number of results, but there was also restrictions of these methods. So today I will give you some overview about these results, which are for classifying non-simple C-star algebras. And more recently, I've also looked into classifying C-star algebras with group action in some equivariant way, which is also interesting, but maybe even more difficult usually. So we have fewer strong results in that case. So if you go towards non-simple C-star algebras, the easiest case beyond the simple case would maybe be just an extension of simple C-star algebras. So let's briefly look at the easy example. This means that you have an extension of C-star algebras, and I and B are simple. And in that case, there is such an equivariant KK theory. These are also, well, so this means that the primitive ideal space of A is just a two-point set. So there's 2 points, and one of them is open. And but only one of them is open, and the whole space is open, and the empty set is open, and that's the topology. And you can use the general KK theory for the situation, or you can also write it down specifically for this situation and simplify the definition slightly. And in a PhD thesis in Münster by Alexander Bonkert, he found out that this works. And his result was that under some kind of nuclearity assumptions, so KK equivalence is the same as an isomorphism between the K-theory long-exact sequences. So for this extension of C-star algebras, we have a 6-term exact sequence involving 6 K groups of these 3 C-star algebras. And if you have two extensions, and if these chain complexes are isomorphic as 6 periodic chain complexes of abelian groups, then they are KK equivalent if they're also nuclear and things like that in a certain sense. So you can classify them using the Keith-Lonitag sequence. This was a result that Bonkert proved kind of by hand. And it's a special case of later results that were proven using this homological algebra machinery. So you can get this and you can get it using some very special generators. Well, if you think about extensions, there are some obvious choices, like you could take just the complex numbers twice and take the quotient to be 0, or you could take this, or you could take the suspension of the complex numbers, put into the cone of the complex numbers, and then the quotient is just, again, the complex numbers, and this thing here is contractible, and here the bound is an isomorphism, and these three and their suspensions give you the generators that you need to produce the UCT. So this is as in Georgi Nadarashvili's talk, so you can now do projective resolutions and check that there is projective resolutions of length 1, and so you get the UCT. And of course, this nice case might suggest that you can do this more generally. However, it turns out that, well, this simple ansatz so if your C-star algebra is coming from some increasing chain of ideals, so of course there's 0, and then you have some ideal, and then the next one, and finally you have something, and then with simple subquotients. So in that case, you can just take all the subquotients of these ideals, and you look at the K-theory of, well, these subquotients, ik mod il, for L less than K. You look at all these K-theory groups and make a diagram out of them. So these K-theory functors are also representable by some suitable C-star algebra of this type. And then if you take the representing objects as your generators and set up the projective resolutions and so on, you find again that there's resolutions of length 1, and therefore you have a UCT and can classify like this. But this is actually almost everything you can do with this method. One of my students, Rasmus Bentmann, also found some kind of converse results. If your primitive ideal space is, well, if you know that this kind of method gives you a universal coefficient theorem, then you have to be close to this kind of situation that I was talking here. There's a slightly more general class where this also works in a similar fashion, but it certainly doesn't work for all even finite primitive ideal spaces. So how to go beyond these cases? And Well, there's different ways how one can do this. In the end, it turns out that two approaches are particularly effective. So one of them is allow length 2 projective resolution. So that's done in one paper by Rasmus Bentmann and me. In that case, the classification is not quite as simple. If you have length 2 resolutions, then you can't just use the obvious invariant that you started with. So this universal approximation that George Tenereshvili talked about, that would be the invariant you might want to use. But if you have projective resolutions of length 2 in this abelian category, then well, they're just obstructions for this invariant to classify, but you can actually write down the obstruction. So there's some specific class in X2, which now exists in this more complicated setting, which when you add it to the information does classify things. So you allow these length 2 resolutions and you add a class which we call the obstruction class in X2 to the data. And another method which also works in almost exactly the same cases would be to use not abelian group valued or module valued, but KK valued invariants. So in the usual UCT, you would ask that there is some isomorphism between certain abelian groups, preserving various maps between these abelian groups. So it's some module category or some diagrams of abelian groups that occur, and you want these diagrams of abelian groups to be isomorphic. Now, what you could try to do instead is take some forgetful functors to KK theory and ask that the diagrams of C-star algebras that you get are isomorphic in the category where you use morphisms in KK as your arrows. And this also has a similar effect of increasing the length of projective resolutions, because in KK theory, you have the universal coefficient theorem. So if you have a diagram in KK theory, then you don't have just maps between the K groups, but you also have these X classes. And there's some extra compatibility between these X classes if your diagram commutes in KK theory. So you have a bit more information, and this extra information turns out to give you the same extra stuff that this obstruction class in X2 would give you when you go further to take K-theory groups, so that these K-equivalent invariants also give you a nice classification result. Okay, and maybe now I should look into some concrete examples of this. And maybe the most understandable case would be Z actions on C-star algebras. So let's turn to another example. The group Z is infinite and discrete, which makes it maybe intuitive to study this KK group. Actually, there is an equivalence between KKZ and KK for the dual group, which is the circle group, called Barsh-Skandalist duality. it's roughly just taking the cross product and equip it with the dual action of the dual group. And this gives you functors going back and forth, which when you go back and forth, give you just stabilization with the compact operators. And that says that they are really inverse to each other up to KK equivalence. So you get this equivalence between the two KK categories. So everything I say for Z also works for the circle group by just using this duality isomorphism between these categories. So the group Z satisfies the Baum-Kohn conjecture, which means that certain things simplify for it. And the correct bootstrap class in this setting this is generated by C0 functions on Z, with Z acting by translation. If you pass to the circle action case, well, you just get the cross product, which is the compact operators on L to Z, which is equivalent to the complex numbers. So the KK endomorphisms of this generator, that's known to be the representation ring of the circle group, which is Laurent polynomials. And well, since this is an equivalence of categories, that's the same as the KKZ endomorphisms of C0Z. In C0Z, I think the X would just be translation by one step. That's how this equivalence goes. Okay, so if you set up your homological algebra machinery, then the universal abelian approximation turns out to be the functor which takes KKZ to countable modules over the representation ring, which is this, and countable Z2 graded. And it's just taking it's just taking the K-theory of the cross product. Or if you pass to KKT, it is taking the ordinary K-theory of the C-star algebra and looking at the action of the representation. Wait a moment. No. No. What am I saying here? It is not taking the cross product, it's just taking the K-theory. Sorry for that. Here it's just taking the K-theory. After the circle action, you are taking the K-theory of the cross product with T, which is the equivariant K-theory. If you take the K-theory of a C-star algebra with a Z action, then the automorphism giving the Z action will give you an automorphism of the K-theory group, which is how X is acting. So this is how you get these modules. Okay, so you have a rather concrete functor here, and this turns out to be this universal abelian approximation. This follows from general theories because we have this nice generator, which also turns out to be compact and things like that, so that all the machinery applies nicely to this situation. And the target category, you see, has length 2, resolutions. But usually not length 1. So you can't expect to have a universal coefficient theorem in the usual sense. At best, you will have this more complicated version for length 2 resolutions. Okay, so this is one way of handling this situation. The alternative way would be that you take KKZ and you take some kind of forgetful functor to KK, I write it in brackets Z, which means that you have, so an object here would be a pair A, comma, maybe call it alpha, with alpha being an element in KK0, A, comma, A, which is invertible. So I make a little cross here. So you have not an automorphism, but you have a kind of KK automorphism. So you forget part of the automorphism, you only remember its KK class. This is, of course, a forgetful functor. The target category is not abelian, but KK is triangulated, and there is a general nonsense construction. For any additive category, you can embed it in some abelian category by a construction of Freyt. And well, if you do this with KK, you get some abelian category, and then you can take automorphisms of objects in that larger category. And so you can embed this in some abelian category. And the embedding is in such a way that these objects are those which are projective and also those which are injective. So in this larger category, this here would be the subclass of projective objects. And this forgetful functor also has some adjoint, and so the homological algebra machinery of projective resolutions actually does work in this setting as well. And the good thing is that in this framework, in KK, the projective objects would be exact. So in this abelian category, maybe I write here with Z. So there was some abelian category, and then you take the pairs of an object in there and an automorphism in that abelian category. And in this original abelian category, the projective object is the elements of KK. If you now add this extra automorphism, so you add one more kind of endomorphism acting on things, then again, not everything is projective, but you have resolutions of length 1 coming from this automorphism. So here you have length 1 resolutions. And the classification theorem now would be a very simple consequence. So first of all, there is a UCT, and then there is the theorem. Let's maybe state only the classification theorem, which is a corollary of the UCT. So if you have alpha is an automorphism of A and beta is an automorphism of B, then A alpha and B beta are KK-Z equivalent. This happens if and only if there exists a KK-equivalence between A and B. So some invertible KK0 element from A to B, so that it intertwines beta and alpha. So beta composed with gamma is the same as gamma composed with alpha in KK of A comma B. Of course, this is also invertible and even. So this is how you can check whether Z actions are KK equivalent. I think this is a nice criterion which follows from this machinery. I don't see any questions yet. If you do it with the length 2 resolution approach, well, the data gets a bit more messy. Maybe I won't give you the details of that for this reason, because in the end, it turns out that you get an equivalent classification result. So, but at the time we wrote this, we didn't think about using KK-valued invariants to do classification. So why, let me choose a different color again for another theory discussion. So why can classification with the obstruction class work? And you could think about the spectral sequence that you get computing the arrows in your category. So there is a spectral sequence. And maybe I just call my category now T. So this is a generic triangulated category. And I want to compute the arrows between A and B, assuming that A is in some bootstrap class. Otherwise, this won't work in these KK theory situations. And you want to compute this, and it involves, well, X P in some abelian category between some invariant. Oh, I shouldn't call it A, maybe I should call it C-like category. So I have f of A, I have f of B. These are my universal invariants into some abelian category for the homological algebra I'm doing. So in the case at hand, it would be take the K-theory of the C-star algebra equipped with the induced module structure over this Laurent polynomial ring, and C would be the category of graded modules countable over the Laurent polynomial ring. And so there's a spectral sequence involving all these XPs on the second page. And by assumption, only P from 0, 1, and 2 occur. And so the only possible boundary map will go from x0 to x2. And the way the spectral sequence works is that if you have an element in x0, which means hom, so you have a homomorphism between the invariants, if the boundary map sends it to 0, that's necessary and sufficient for the existence of an arrow in this T that gives you this x0 thing. And so by looking at something in x2, you can decide whether a specific map between the invariants lifts to your category. And if you can lift it, the lifting tends to be invertible because the inverse map will also have vanishing image under this kind of second boundary map construction. And so you have now maps going back and forth, which induce this isomorphism on the invariant. And since you're in this bootstrap class, that's good enough to be an isomorphism in the category T. So in order to lift an isomorphism on the invariants, you just need to know that the second boundary map sends this isomorphism to the zero element. And there is some kind of absolute invariant in X2 of, so there is a class delta A in X2 of f of A. Well, there's a degree shift here. Maybe I should write suspension or write this 1 in brackets to mean the dimension shift here. And there's also a similar delta B for f of B, and an isomorphism that goes to 0 in X2 exists. So an isomorphism f of A to f of B. That exists if and only if there is an isomorphism. An isomorphism I wanted to add here that goes to 0 in X2 of the appropriate things, if and only if there is an isomorphism that when you apply it to delta A in the appropriate well, it maps delta A to delta B. So this delta A is some extra invariant that you can attach to your object in this triangular category. And an isomorphism lifts if and only if it maps this obstruction class to the other obstruction class. This result actually was first developed in the theory of spectra, module spectra, and so on. And then Rasmus told me about this result, and we thought we should carry this over to our, or carry over, apply it to our setting and maybe prove it by hand so that we can convince the C-star algebras that they don't, well, that this works without using any homotopy theory. And so we could use this to classify C-star algebras. Okay, so I've now given you some rough idea how these classification methods work. I think these are the kind of powerful methods that you can use to classify non-simple C-star algebras. And both methods actually work for many examples. So the two ansatzes, which maybe I should retro back to them and say what I mean with the two ansatzes. So one was to add, well, to allow length 2 projective resolutions, and the other one was to use KK-valued invariants. And both of these ansatzes work in the following cases. So I already mentioned these Z actions, or equivalently circle actions. Then they work for all graph C-star algebras with finitely many ideals. So the point here is that if you have a graph C-star algebra, this is an important, much studied class of C-star algebras, then there's a specific method of computing their KK theory and these things, which, if you think about it, shows you a length 2 projective resolution in the appropriate equivariant KK group for this specific object. So it's not that every C-star algebra with finitely many ideals has a short length resolution in the appropriate equivariant KK theory, but for graph algebras this is true. And if you treat general C-star algebras, then C-star algebras where the primitive ideal space is some finite space, and it's what's called a unique path space. So X is a finite topological space. You can describe the topology on that just a finite space by a graph. Just look at the closure of points and what they contain, and this gives you a graph. And if this graph has the property that between any points there is at most one path, I think it's okay if it's disconnected. That's just means it's direct sum, so that's harmless. But there shouldn't be more than one path between any 2 points. And if that is so, then you can use the unique path space property to write down explicit length 2 resolutions over the over a certain invariant. So the appropriate so the ring whose modules are diagrams over this graph has length 2 resolutions. And if you use KK-valued invariants, then the length goes down to 1. So those are the 3 cases where this method works nicely. And since I still have some time, I might also speak briefly about classifying group actions. That's kind of a different topic. And when I say group actions, let's talk about actions of Z mod P for a prime number P. So this is work of my doctoral student, Manuel Köhler. But recently I took this up again and let's say did some algebraic computations, so classifying actions of Kirchberg algebras. So Manuel Köhler found the UCT in this case. Using a specific generator for the bootstrap class in this situation. So then you have a UCT, so you know that the objects in the bootstrap class are, well, just equivalent to isomorphism classes of modules over a certain ring. And that was kind of his end result for this question. But then the question is, what are those modules? And there's an extra twist here, namely, when you use the when you do it for the usual KK theory with the usual UCT, then all abelian groups occur as K groups. But here you don't get all modules. You get modules which have a certain extra exactness property. So if you take the invariant of Manuel Köhler for an action of this group on a C-star algebra, then always this invariant contains a certain exact sequence, even 2 exact sequences. And so you can only hit things where you have these exact sequences. And so then and all these exact modules, so I call a module exact if it has these exact sequence, all of them actually arise. So you know the range of the invariant, but it's not all modules. So what you find is that Z mod P actions in the bootstrap class, in the equivariant bootstrap class, up to KK Z mod P equivalence. These are in bijection with, well, exact modules, shouldn't say exact graded modules, it should say exact modules over, well, a certain Z2 graded ring R, and I should also add countable, because I only get countable things in this way, because I assume separability. And of course, here it's up to isomorphism. So this was Manuel Köhler's result. And so my own work started with the question, knowing this result, how about actions on Kunz algebras? So in the Kunz algebra case, you assume that a specific ingredient in this module is the case of a Kunz algebra, so it's a cyclic group. The case of Kunz algebras is well known, and it could be any cyclic group, including the trivial group, or even also Z. So when you look at actions on Kunz algebras, then you get those exact modules where one of the ingredients is a cyclic abelian group. And now you wonder, what kind of modules do you get? And I thought this question should be looked at because more recently people have been trying to classify these group actions and, well, maybe assuming extra conditions like Rochlin properties, they got some nice results. But beyond that, it seemed pretty difficult. There were also good results in the torsion-free case or good conjectures, which are now actually results, in part also thanks to my work on this. But in the torsion-free case, it looked much more difficult. And so it is much more difficult because even in this rather harmless-looking case of a prime-order cyclic group, you can still do it, but the result is, let's say, very complicated. So in the computation, I got a complete result, but the result was that there is kind of 11 or so different series of examples, each of them structurally different. Proving that there's only those 11 cases, well, is a long kind of case-by-case study. So you take the exact module, and then you have certain maps which form an exact sequence. And one of the ingredients in the exact sequence is just a cyclic group. And so the map on a cyclic group is either injective or zero, things like that. And then you have some cases to look at. And you carefully look at all the cases and arrive at these at roughly a dozen or so different possibilities how these modules might look like. And I don't think I would use my time to explain the outcome, what these 11 or 12 different series actually are, because it's just complicated. And I wrote it down because I thought I should, just to be specific, but it was a rather painful exercise, I admit, to write all this down. It's not the kind of math I usually like to do. I wouldn't say that classifying these kinds of actions is a nice exercise for a student. It gets pretty complicated. It seems more like a question for computer-assisted proofs, maybe, to look at all the possible cases and then figure out how they could look like. The only case that was quite tractable was the case when P acts invertible. So the result is simple. So here P means P times identity. So multiplication by P could be invertible in this KK ring. or you absorb the appropriate UHF algebra that's equivalent, as was discussed in Georgi's talk. So in that case, I can write down the result quite nicely. But before I can do that, I should first write down Manuel Köhler's invariant and then say how it goes in this particular case. Or so there are 3 Z2 graded modules, of course, all countable. And one is just over Z, and 2 are over, I should have said Z adjoint 1 over P, because I want P to be invertible, and 2 are over the cyclotomic extension of that. So you adjoin a primitive P's root of unity to the integers, and you also adjoin 1 over P. And you have 2 modules over this thing. Well, actually 4, because they're also Z2 graded, so there's the even and odd part. And then there is also such a Z2 graded module over the integers adjoint 1 over P. And why could this be relevant? Well, if you think about the group ring of this cyclic group, well, and you adjoin 1 over P. So this would be the endomorphism ring of the complex numbers when you adjoin 1 over P. And this thing is isomorphic to the integers for the trivial representation, direct sum with this cyclotomic field. Because you can do this decomposition of the of this root of unity polynomial x to the p minus 1 into x minus 1 and the other factor. After inverting p, this works. And so you can get the direct sum decomposition of these 2 rings. And so this is roughly the reason why this kind of ring might be relevant. And it turns out that you need exactly these 3 ingredients. Now, to end my talk, let me sketch how Manuel Köhler's invariant looks like. What are his generators? So Köhler's generators are, well, there's the complex numbers with a trivial action. Then there is the functions on Z mod P with a translation action. And then there is also the cone of the inclusion of C into functions as a constant function. And you adjoin this cone to get to get resolutions of length 1. Of course, this cone belongs to the localizing subcategory generated by these 2 things, but you add the cone in order to get resolutions of length 1. So it tames the homological algebra. And those are the 3 generators. And so Manuel Köhler's ring, which I called R, would then be the KK Z mod P endomorphism rings of the direct sum of these 3 generators. And you can compute this explicitly in terms of generators and relations. This was already kind of done by Manuel Köhler, but I added some maybe niceties to the computation, wrote it down again in my own paper. So you can find a nice description of this ring over there. It is already pretty complicated, but not yet unmanageable. Since you have these three generators, kind of by definition, there's a tuple sequence in both variables. And so if you take the invariant, namely maps from this generator, let's say D, into some other object, then of course there is one exact sequence you can see immediately. There is another very important fact, namely there is also another way how you could take a cone. You could embed these functions into the compact operators on L2 of this group as diagonal matrices. And this is Morita equivalent to the complex numbers. And there is also a mapping cone for this situation. And it turns out that up to suspension, this mapping cone and the other one are KK equivalent. So these two different cones, so the cone of this would be the suspension of the cone of this inclusion here. This is kind of a miracle in Manuel Köhler's work. I found maybe a slightly better explanation for this. Well, using duality for functions on manifolds. So this is just, well, embedding one point into a bunch of points. But if you do this in a slightly different way, you can also get this, well, you can get this by taking away a few disks in a bigger disk. And so you get a nice manifold model for this cone, which is good because for manifolds, you know duality in KK theory. And this also allows you to relate it to this cone here. But I think my time is up anyway, and maybe I just leave it at the fact that these two cones are the same. That is actually quite important. This is a result which, at least to me, seems to be a C-star algebraic result because it's based on kind of this duality taking cross products by Z mod P. I'm not sure this would be a true statement if you work in a more homotopy theoretic setting. Maybe it has to be if the bootstrap class in an equivalent KK theory is equivalent to well, some category of modules, module spectra, but I'm not sure what this equivalence would amount to in a homotopy theoretic context. Maybe some people here know more about this. And so let me summarize. I explained to you, gave you a survey of various results on the classification applications of homological algebra in triangular categories. So sometimes you can choose generators carefully to make a UCT. Sometimes this involves not abelian group valued things, but you take KK theory valued invariants to kind of go to more complicated situations like general graph C-star algebras or actions of the circle or the integers. There's also a method if you have length 2 resolutions. And in all these cases, you get nice classification results up to equivalence in a suitable KK theory. And, well, I'm now open for your questions.
Let's thank the speaker. Yeah, Jonathan.
Yes, no, Ralph, really nice talk. So I had a couple questions. So first of all, while you have this last slide up here, so this KK Z mod P is a kind of interesting case because Sakai duality is a kind of involution on the category because of the fact that Z mod P is self-dual. So that would work for any cyclic group, but not for not necessarily for other things. So this, the fact that these two cones are suspensions of each other is sort of related to that, isn't it? That's question number one.
Yes, I think so, yes. Although actually I'm maybe not related to that. it's more that I'm using this involution to simplify computations. So since this cone is isomorphic to the suspension of the other cone, and since this involution by cross product flips my two generators, it will also flip the two maps. So the inclusion of diagonal into compacts is actually the Takai duality from this inclusion of C into C of Z mod P. So my ring carries an automorphism, which exchanges the roles of my two generators C and functions on Z mod P.
Right. Yeah. That's
And
what
leaves the third one the same up to a suspension. And so this halves to some extent. This means that you have to do only half as much computation, which is sometimes nice.
Okay, and then the second question is sort of a joint question for both you and Ivo. So, I mean, thinking about your two talks being back to back, I was wondering if, the TT category geometry of KKX is accessible, say, for X a finite space. I mean, the first case to do, of course, is the case of 2 points where they're, with a T0
I
topology.
think this should be a question for George Nalarishvili, actually, because in his thesis, he worked on exactly this kind of topic. There are some complications because this KKX is not a tensor category unless X is Hausdorff. So if you have continuous fields
right.
of
Yes.
space,
Okay. All right. Yeah.
you can, of course, tensor them together, but if you have a non-Hausdorff space, this doesn't work like that.
Mm-hmm.
So you have to classify something else, like maybe localizing subcategories. That makes perfect sense without tensor. And there are some results, but well, if you want to know more, please ask George for it or read his paper. I would rather not say anything about it right now, since George is in the audience and he's the expert on this topic. One thing I remember still is that the lattice that you get isn't necessarily spatial. So the localizing subcategories, of course, always form a lattice, but not all lattices are open subsets in a topological space or even embeddable in the space. So this one actually gives
it's
you
not distributive, so it's as I
Not
remember, it's
distributive.
in like lattice, so it cannot come from the lattice of some set, like power set. Yeah.
Okay. So that was the reason for that. Yeah. So I say no more about that question. Who else has got questions?
I have one. May I ask?
Yeah.
So, I mean, you have this ring of Manuel Köhler. And so, I mean, this ring has somehow three projections, yeah? Or I mean, or at least two projections
Yes.
onto the first two summits. So now, I mean, that is just related to my problem of calculating these homotopy groups of the K-series groups of these cross products of cyclic of powers. So, I mean, assume that you have a module over this ring and you just know, say, something about the image of the first projection, say, on the, I think the trivial, not the trivial thing, I mean, the projection corresponding to the functions on the group. Assume you know this. So how much can you say about the module?
If you know only one of the three pieces, it's not too much. So you have an exact sequence. So in the end, there is, so you have maybe three ingredients, X, and then there's Y, and there is Z. And no, not integers, it's just a third ingredient, that's the usual Z. And then there is again a map to the, well, X with a degree shift. And this is an exact sequence. And there is also another exact sequence where you have arrows going the other way around. And then if you go back and forth with these different classes of generators, then you get some specific elements in the group ring acting here. So on X and Y, you have just the group ring of Z mod P. On Z, you have kind of two copies which are merged together in a complicated way. And going back and forth gives you two generators for these two group rings with some relations among them. So it's not a very simple ring. And well, if you know one piece in this exact sequence, and if you might know it is very simple, like a cyclic group or something, then you get good control on the rest in the sense that there's maybe 11 or so different series, plus the divisible case. So what you can always have is something like 0, and then something, y, and then the same y here, and then again 0. And if y is divisible, this works.
No, I mean, I'm interested in the p torsion case.
Yes, and with p torsion, then at least these things can't happen. But still, well, let's say if you know that this ingredient X here was something like z mod p to the n or something, then there's a bunch of cases, and the number of cases up to this divisible case is finite. I think in some of the cases that you find in my paper, the y and z might also be integers and not z mod p to some higher power. So maybe you can rule out some of these cases, but I think there's still a finite number of possibilities, even if you know so much about this ingredient. And if it's not cyclic, so it's getting bigger, then I would guess that there's more chances of these to get complicated. And I didn't go on after that. So I think knowing just one piece isn't enough information to get along, unless you have some very special circumstances.
Okay,
I'm not
it's
sure
a
what the
pity.
action of the grouping on this. Maybe if that's if you're very lucky, this might give you more constraints on the other cases, but I wouldn't be very optimistic there. Any more questions?
Okay, let's end the recording.